Hello everybody, welcome to General Chemistry, semester number 1. This is chapter 0, so this would normally be our welcome day where we talk about what we need to succeed in the class. You definitely need math skills. Algebra is going to be important. We need to be able to manipulate equations like the density equation. So we need to be able to solve that density equation for anything. So volume times density is equal to mass, and volume is equal to mass divided by density. So all of these are through algebra by manipulating that one equation. You're going to have to work hard and you're going to have to read carefully because this is an online course. I am not an instructor that's going to hold your hand and walk you slowly down the path. So if that is what you're looking for, you may want to find a different instructor. There are some out there. I expect that you're going to read and understand and ask questions for what you don't understand. So if I keep pointing you back to something, it's because I can tell that you haven't actually read it. I'm not going to read it for you. I'm not going to do it for you. You have to do the hard work for yourself. Also, try to keep a positive attitude because that's going to be something that's going to get us all through this time. So again, read carefully. There's a lot of word type problems in chemistry. We're trying to lay the scene of, this is what happened in lab. This is the data that you got. How do you interpret that data? So you're going to have to find what information is given and see what is being asked for. Then you have to find the appropriate equations, constants, and conversion factors. You want to also check the sign, the units, and significant figures before completing your answer, and make sure it's reasonable. So this is something we should always be doing in life and double checking before we hit equals or enter or say that this is our final answer. So this is a suggested chapter problems from your textbook. If you're looking for something up and above the mastery homework that you have, this could be helpful for you. And most of the answers are in the textbook. If they're not, feel free to ask about it. That's what our class time is for, is to ask questions and work through problems. So starting off then, the scientific method. The scientific method is a set of guidelines that the scientists follow to perform experiments. Before we came up with the scientific method, people had all different types of ways of doing their research, and we had no way to really tell what research was good research and what research wasn't, and what was valid and what was invalid. So now when we follow these steps, we get clear, valid data, hopefully, as long as people aren't lying, and then we're going to retest it. So the first thing that happens is somebody makes an observation. So they make an observation and then they think maybe, why does that happen? So an observation, you think, why does that happen? And you try to explain why it happens. That part where you try to explain is called a hypothesis. So that's a tentative or short term. So tentative means short term, or we're trying this out, explanation for why you think the observations happened. Then you design an experiment to test the hypothesis. Now, one thing they don't teach us in grade school all the time that well is that negative results are just as important as positive results. We need to know the things that don't work just as much as the things that do. So one thing that's going to be really important right now during this pandemic is making a vaccine. So talking about the very first vaccine that they ever came up with was for smallpox. So smallpox was a pandemic. Now that we're all familiar with how unfortunate and how not fun pandemics are, somebody during the smallpox pandemic observed that milkmaids don't contract smallpox. And if they did, on the rare occasion that they did, it was not as lethal. They didn't die as often. So somebody said, well, a lot of times milkmaids get cowpox from the cows that they're milking. So having contracted cowpox, which is less lethal, the milkmaids have a natural immunity to smallpox. So they underwent an experiment and intentionally exposed a healthy child to cowpox, let him get better from the cowpox, and then intentionally gave him smallpox. Okay, this is not how we do things now. You'll notice there's a lot of trials and then there's human trials, and that's what's taking so long to create these vaccines is we can't just test them on humans and hope that they work. But this guy actually tested it on his own child, and because the child did not contract smallpox, he was immune to smallpox. We now inoculated people with smallpox vaccines, which actually came from cowpox. So they gave him the cowpox virus, confirming that this model works. So VACA actually means cow, and that's where the first vaccine came from. So vaccinations are important, including the flu vaccine. And you know what? If I have a chance, my kids will be and I will be first in line to get a vaccine that comes out for COVID. So what do we do with this data that we get? What kind of data do we get? Well, there's different types of data. There's those that are physical, and then there's things that are going to be quantitative, and there's qualitative. So we have physical, chemical, and we have quantitative and qualitative. So physical and chemical are actually types of properties. Quantitative and qualitative are types of data. Data is actually a plural word. So quantitative, it has a quantity. It has a number and a unit. Qualitative, quality, is from our senses. See, smell, taste. Don't taste in the lab. Not in lab. Feel. So our senses are what we're going to use for qualitative data. Quantitative data is going to be those sets of data that we get that have a number. And if I remember correctly, how to get rid of this. There we go. All right. So when we have quantitative data, we need to have some way to measure each type of unit, and each type of quantity is going to have a unit, and what units we use are determined by what system of units we're using. Now there is an international system of units, which is a revised metric system. So this was designated in 1960 for use by scientists. This is what we mostly use. There are 7 base units. For mass, we use the kilogram. Mass is how much matter is present, which we'll go over in a minute. Length is how long something is. We use the meter, lowercase m. Kilogram was lowercase k, lowercase g. Temperature is Kelvin. Notice it's a capital K. It's not like degrees Celsius or degrees Fahrenheit. It's not degrees Kelvin. It's just Kelvin. There is no degree symbol there. Amount of a substance is the mole, MOL. That dropping that E saves us a lot of time. Time is the second. Electric current is the ampere, capital A. And luminous intensity, I can't underline that one, doesn't want to let me, is the candela, which is actually based off of candlelight. Now we're not really going to use this one that much. This would probably be used a lot more in physics. I'm not saying it won't come up in chemistry, but probably not as much this semester. So let's go through each one of these. You do have to be familiar with the metric system. I do assume that you've had some metric system before. If you haven't, it's pretty easy to learn. So you can teach yourself through the videos that are posted online. You can Google it, you can YouTube it, whatever you need to do. One of the mnemonics is King Henry drinks much dark chocolate milk. So King Henry drinks much dark chocolate milk stands for kilo, which is here, hecto, which is here, deca, here, meter, which is the base unit, which is actually right here and it's not listed, deci, centi, milli. Now, these ones are all powers of 10. So if you look here, it's 10 to the third, 10 to the second, 10 to the first. That means this is 10, this was 100, this is 1,000. This is 1/10, this is 1/100th, and this is 1,000th. So you take your number, whatever, if you have 10, and we're using the meter as the base unit, 10 meters, how many decimeters do you have? You would say, well, this is 1/10, it's smaller. So I would say 10 meters. There are 10 decimeters in 1 meter. And I would multiply it by 10, and that would give me 100. So there are 100 decimeters in a meter. Whereas kilometers here, we would say in 10 meters, for every 1 kilometer, there are 1,000 meters. That's how I like to do it. You can do these however you want. So we're dividing this by 1,000. So what would that be? 0.01 or 1/100th of a meter. Now, I would prefer not to see the fractions. I want you to actually do the math and give me the decimal. So that's how you're going to do those. We're going to set those up. Those are conversion factors. Once we get past this block here, we go up by threes. So 10 to the minus 3 is milli. Micro, notice this mu. This is going to be important. These small ones are important in chemistry because there's a lot of really small stuff in chemistry. So micrometer or micrometer, people like to say micrometer, is times 10 to the negative 6th, the very popular one. Nano times 10 to the negative 9th. And I know I'm old, but this show was old even when I was young. There was a show called Mork and Mindy. And it was Robin Williams. And he was an alien from another planet. And I always remembered when I was a kid, there were 9 planets. And he used to say, nano, nano. That's just what he said. Don't ask me. I don't write this stuff. Okay. So that's how I remember that one, but that's up to you. Micro is -6, pico is -9, or sorry, micro is -6, nano is -9, and pico is -12. Femto is also popular, but I would say that these three are probably things that you should know at this point. Between like microbio and chem, they're pretty popular. Also, this top end of the scale is probably something you're familiar with just by talking about computers. You know, we all have a terabyte something somewhere, right? We used to have, I hate to say how far back it was when I started with computers, but kilo wasn't really in the title. We used to have megabytes and kilobytes, right? So we had kilobytes, then we had megabytes, then we had gigabytes, now we have terabytes. So I've come a long way in my computer literacy, but that's where those top end of the scales are coming from. We probably hear a lot about those in technology. Mass is the amount of matter in an object. What is matter? So what is matter? Matter is anything that has mass and takes up space. So it can't just have mass, it also has to take up space. We talk about different things. You know, is a balloon matter? Yes, it is. It's got air, and that air takes up space inside the balloon, things like that. So matter is anything that has mass and takes up space. And oh yeah, look at that, it was written there. The SI base unit is the kilogram, but most commonly we use the gram and the milligram in lab. Unless you're working in an industrial lab, you might make things on a larger scale and be using stuff like the kilogram. So the quantity of matter an object contains is going to be the mass of that object. Mass and weight are not equivalent, especially if you're talking about space science. So mass is constant. It doesn't change. If I take my mass here on Earth, so mass on Earth and the moon are the same. But my weight on Earth is higher than on the moon. Why? Because of the pull of gravity. So weight depends on the amount of mass, how much matter is in that object, and how much gravity is pulling it down. So we have both of those quantities together, and the pull of gravity is less on the moon, so the mass would be the same, but weight would be different. So this is an analytical balance. This is a top-loading balance. I like to usually just at this point tell you how much these cost. So whenever our quantity or quantitative analysis doesn't matter as much, we try to use this balance because it's cheaper. This one is much more expensive. So this one costs anywhere from, you can actually even get higher ones of these ones, but most top-loading balances are a couple $100. This analytical balance costs anywhere from $2,000 to $10,000. Now, sometimes those prices go down as we get better technology, but the analytical balances are expensive. So if you find yourself in a chem class later, take care of all of your balances always by brushing them off and cleaning them off when you're done, just because it's good lab hygiene. But also, then your student fees won't go up because you're wasting money by ruining balances. Length is something you've probably been measuring for a long time, but we've probably been measuring it in inches, right? Inches and feet. Goodbye, English system. We are using the metric system. So the SI base unit here is the meter. A meter, so 1 meter is approximately 3.3 feet. The most common we're going to use are meters, centimeters, millimeters, micrometers, nanometers, and picometers, depending on what we're talking about in the class, but those are very common units. Definitions for the meter have changed over the years. Back in 1790, it was defined as 1/10,000,000th of the distance from the equator to the North Pole. In 1889, it was the distance between two thin lines on a bar of platinum iridium that was stored near Paris, France. They didn't want to tell people the location because they wanted it to remain there. They didn't want anybody to steal it. And now, in 1983 to current, it's the distance traveled by light through a vacuum in 1/299,792,458 of a second. Wow, right? Okay, so hopefully we all know how to measure length. Temperature, we're used to measuring in Fahrenheit. Stop being used to it. We're going to measure in Celsius. So Celsius is where it's at. You do need to know that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius for this. So you must know this for this class. Kelvin, you're going to do this a lot with gases, but we might do it before then. So we're going to need to know how to convert from Celsius to Kelvin. So you take the Celsius degree and you add 273. Technically, it's degrees Celsius plus 273.15, but it's okay if we just use 273 for this class. It'll be all right. The lowest possible temperature in theory is 0 Kelvin. Now, there was some movement on this in the last few years where we came really close as scientists in a lab. I say we, I wasn't involved, but they came really close in a lab to, I think, within thousandths of a degree, I think it was. I can't remember exactly, but very close. They've seen particle motion slow down, but never stop. And they, at this point, don't believe that we can actually reach 0 Kelvin to prove that particle motion would stop and that all life as we know it would not exist at 0 Kelvin. So it's still in theory. Celsius and Kelvin are equal in magnitude. I'll show you a thermometer on the next page, which will show you that. But the English system, the Fahrenheit system is not. In general, the English system is not good overall. To go from Celsius to Fahrenheit, you have to take 9/5 times the Celsius degree plus 32 to get to Fahrenheit. Some people, like maybe, I don't know, me, keep their car in Celsius and make people convert. Haha. But if you want to go from Fahrenheit to Celsius, you got to remember your algebra. So we would take the Fahrenheit degree, we would subtract 32, and we would multiply by the inverse, so we would multiply by 5/9. So isn't that fun to get to degrees Celsius? So those are equations I would give you. So I'll give you the equation if you need it, but you might have to be able to do the math. You would have to be able to do the math for that equation on your own. So this is temperature. We said that Kelvin and Celsius are, what did we say? Go back. They are equal in magnitude. So equal in magnitude, that means every degree that I go up 1 degree. So 0 degrees Celsius is 273 Kelvin. 1 degree Celsius is 274 Kelvin. But 32 degrees Fahrenheit is where this water freezes, right? They're actually all equivalent at 40, I believe it is. But 32 degrees Fahrenheit, if I go to 33 degrees Fahrenheit, I would subtract 32. I get 1, right? Is that what we're doing here? Yeah. 1 degree. Then I'd multiply that by, go back here. This is the equation I'm doing right here. I would multiply that by 5 to get 5, and I would divide by 9. So this would be 1.8 degrees. So every time I go up 1 degree Celsius, I'm actually going up about 1.8 degrees Fahrenheit. So they are not equal in magnitude. Like these two are. These are equal in magnitude. So these thermometers show all the freezing points at all the different temperatures and the boiling points of water. So this is the freezing point and melting point, or boiling point, same, melting point / freezing point, boiling point, or condensation point, depending on which way we're going, of water. Volume is our derived unit. 1 cubic meter is equal to 1,000 cubic decimeters. So something we use more commonly is the liter. Where does this come from? So this is 1 cubic meter. That means that this is a cube, right? We all learn how to draw a cube in school, something like this. And this cube is 1 meter high, 1 meter wide, and 1 meter deep. Volume is length times width times height. So length, width, height, or whatever, whichever one you want to label. So we always have a unit that is cubed. So if it's 1 meter times 1 meter times 1 meter, algebra tells me that's going to be 1 meter. 1 plus 1 plus 1, because we add the exponents, would be cubed. So 1 meter cubed is equal to 1,000 decimeter cubed. So that means within this green box here, this green cube, there are 1,000 of these blue cubes, which are 1 decimeter long by 1 decimeter high by 1 decimeter wide, giving us cubic decimeters. There are 1,000 of them. And within this blue cube, there are 1,000 of these red cubes, which are 1 centimeter by 1 centimeter by 1 centimeter. So, have you ever heard of a CC? I'll get 100 cc's of yoo-hoo, please. That CC stands for cubic centimeter. or which is also equivalent to 1 milliliter. So when we're going from cubic units to cubic units, we actually have to do that conversion 3 times. But going from cubic centimeters to milliliters, these are equivalent, so we can get into liters without having to do that conversion 3 times. So volume is something that we will use a lot. This is a volumetric flask. These are used a lot for dilutions and making solutions, making standards. So filling it up to the meniscus is at this line would be 50, from this one would be 50.00 milliliters, and it gives us 4 significant figures. And we'll talk more about significant figures in the significant figure video, but that gives us 4 significant figures. A syringe, depending on how it's graduated, would give us 3 to 4 significant figures. A graduated cylinder like this one, which is, let's see, the graduations go from in ones. So if it's graduated to ones, we estimate to the tens place. So we would get 1 decimal. So we have different ways of measuring volume in chemistry. This burette would give us 2 decimal places. So usually you get 4 significant figures, which are important. So we would want to use anywhere we can get the most significant figures from our measurements whenever possible. And last type of unit we're going to talk about is energy. And energy is the capacity to do work or supply heat. So we talk about energy a little bit. We don't cover it as much in this semester. We'll cover it more in next semester. But we do mention energy changes, where energy goes. When energy, I can spell, leaves the system, it's going to exit the system. It's exothermic. So exo means leaves or exits, right? Thermic, therm means heat. So heat leaves. If it enters a system, it's endothermic. So endo means goes in, into. So heat comes into the system, because remember, therm means heat. So we can break these words down. So we will talk about energy entering and leaving a system. We're going to talk about a little bit about that, but we're not going to focus as much on the calculations form of that, more on the terms of where is it going and what's happening to it. But the base unit for that is the joule, but in America, we like to make things as confusing as possible, so we use the calorie. Well, if you look at a nutrition label here in the US, you're going to see, there's 180 calories. But if you looked at that same label, nutrition label, anywhere else, you would see that there's 180 kilocalories. How does that work? Well, you see this C? It's a capital C. 1 capital C calorie is equal to 1,000 little c calories. If for some reason we're doing calculations with calories, I will not accept trying to differentiate between your capital C's and your lowercase c's, and instead we're going to act like chemists and the rest of the world and use the small k, which means kilo. So we have kilocalories, which is 1,000 calories. So 1 little c calorie is equal to 4.184 joules. 1 large c calorie is 1,000 little c calories, which is equal to 1 kilocalorie, which is equal to 4.184 kilojoules. But most of all, right now, we want to remember that energy is always conserved. It cannot be created, it cannot be destroyed, but it can be converted from one form to another. So we can convert it, and we do. As humans, in chemical reactions, we convert this energy. Well, this video was already a little bit longer than I wanted it to be, but this is where I'm going to stop this video. There will be 2 more videos for this chapter.